Here's a real-time data challenge that's everywhere in the tech world. Find median from data stream. It's a Pattern Mastery 100 classic and a favorite at Google, Amazon, and Facebook because it tests your knowledge of heaps, streaming algorithms, and dynamic data structures. Over 40% of candidates get stuck designing for both fast inserts and instant median queries. Let's make sure you're ready to impress. Let's conquer Find Median from data stream using the basic approach, a proven strategy for building robust, interview-ready solutions to complex streaming problems. Let's break it down. Design a data structure with two methods. Add an integer to the data stream. Return the median of all current elements. Input, sequence of numbers, one at a time. Output, the median after each query. Here's a real-world example. Suppose you're building a live dashboard for financial transactions, and you need to report the median transaction value in real time, no matter how many numbers arrive or what order. Interviewers might ask, how would you design a system to track the real-time median in a large, ongoing event log? Let's assess it. What's tricky? Median queries must be fast, O1 or O log n, and so must inserts. You need to handle an unlimited number of incoming numbers, so no sorting or rebuilding the list each time. Keeping the data split evenly for medians is the key. Think step by step. Use two heaps. Max heap, left side, stores the smaller half of the numbers. Minute heap, right side, stores the larger half. The max heap lets you instantly get the largest of the smaller half. The min heap gives the smallest of the larger half. Balance the heaps so that their sizes differ by at most one median. If both heaps have the same size, median is the average of the two tops. If one heap is bigger, median is its top. Let's go deeper. When adding a new number, if it's less than or equal to max heap's top, add to max heap, else, min heap. Balance, if any heap has more than one extra element, move its top to the other heap. This balancing act ensures that extracting the median is always O1 or O log n. Edge cases. First number, just add. Even or odd total numbers, median logic switches accordingly. Duplicates and negatives are handled naturally. Here's the structure. Initialize two heaps, max heap, invert values for Python's min heap, and min heap. On add num. If max heap empty or num is less than or equal to top of max heap, push into max heap. Else, push into min heap. Rebalance if heaps differ in size by greater than 1, on find median. If size is equal, median is average of tops. Else, median is the top of the larger heap. Now let's implement the sorted list approach, inserting each new number in order so we can compute the median directly from the list. We start by importing the bisect module. This gives us a handy tool for inserting numbers into a list while keeping it sorted automatically. This class will store numbers as they come in and compute the median at any moment. Our constructor sets up the data structure. We keep one list, always sorted, to store all incoming numbers. Think of it like a growing, neatly organized shelf of values. This function handles the arrival of a new number in the stream. We use bisect.insort to insert the number into the correct position to keep the list sorted. No manual sorting, no reordering, Python handles it for us. This operation runs in ON because inserting requires shifting elements. This function calculates the current median from our sorted list. We grab the number of elements in the list. If the count is odd, the median is simply the middle element. We return that middle value, making sure it's a float. If the count is even, the median is the average of the two middle numbers. We compute that average and return it. And that's how this algorithm works. It first maintains a sorted list using binary insertion, then reads the median directly from the middle of the list. Simple, intuitive, and effective for moderate data sizes. Let's check. These operations describe the following sequence. Median finder create a new data structure. Add num1 add num2 find median add num3 find median again. With the sorted list plus bisect approach, every time we insert a number, we place it in the correct sorted position. Let's track the internal list step by step. Is start, after add num1 insert 1 list becomes 1 after add num2 insert 2 in sorted order, 1, 2 find median current numbers, 1, 2, even count equals 2 median equals average of middle two values. Middle values, 1 and 2, 1 plus 2, 2 equals 1.5. So the median is 1.500000. After add num3 insert 3 into sorted position, 1, 2, 3 find median current numbers, 1, 2, 3, odd count equals 3 median is the middle value 2. So the median is 2.000000. Putting it all together, the outputs are null, 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 1.50000, null, 2.00000. And that's exactly what our implementation returns. So, our solution is correct. Keeping the list sorted and using bisect to insert ensures we always compute the median accurately from the current ordered data. Now let's implement the two heaps method, balancing a max heap and min heap to support fast insertions and constant time median retrieval. We import Python's heapkey module, which gives us a min heap. We'll use a neat trick to turn one of these into a max heap. This class will maintain a running median using two different heaps. We set up both heaps inside the constructor. This heap represents the lower half of all numbers. We'll store values as negatives here so it behaves like a max heap. This method adds one new number into our two heap system. We first push the new number into small, but as a negative value, turning the min heap into a max heap. We then pop the largest value from small and move it into large. This ensures the two heaps stay ordered correctly. All values in small should be less than or equal to all values in large. If large ends up with more elements than small, the two sides become unbalanced. We always want small to be the same size or one element larger. So we move the smallest element from large back into small to restore the balance. This method returns the current median from the two heaps. If small has one extra element, that extra element is the median, because it's the largest value in the lower half. We return the top of the max heap, remembering to flip the sign back to positive. If both heaps are the same size, the median is the average of the max of the lower half and the min of the upper half. This gives us an O1 median lookup. And that's how this algorithm works. It first inserts each number into a balanced pair of heaps, then reads the median straight from the heap tops. Blazing fast for streaming data. Efficient, balanced, and elegant. Now we check. Now we'll run the exact same sequence, but using the two heaps approach. A max heap for the lower half of the numbers. A min heap for the upper half. We keep them balanced so that either both heaps have the same size, or the max heap has exactly one more element than the min heap. Let's walk through the operations. Start. Max heap, low, equals, minute heap, high, equals, add num1. We insert 1 into the max heap, lower half, heaps. Low equals, 1 high equals, add num2 compare 2 with top of max heap, 1. 2 belongs to the upper half, so it goes into the min heap, heaps. Low equals, 1 high equals, 2 find median. Both heaps have the same size, 1 and 1. Median is the average of max of lower half 1. Minute of upper half 2. Median equals, 1 plus 2. 2 equals 1.51.500000. Add num3 compare 3 with top of max heap, 1, and min heap, 2. 3 goes into the min heap high equals, 2, 3. Now sizes. Low equals 1, high equals 2 unbalanced. We rebalance by moving the smallest element from high, 2, into low. After rebalancing, low equals, 2, 1. As a max heap top is 2 high equals, 3 find median. Now the max heap, low, has one extra element. Median is the top of max heap 2.0000000. So the outputs for each operation are again, null, null, null. 1.50000000, null, 2.00000, and this matches perfectly. So, our two heaps implementation is correct. It maintains a balanced split of the data stream and retrieves the median in constant time, even as new numbers are added. Real-time data never waits. Find median from datastream shows whether you can keep inserts fast and still answer median queries instantly. A perfect blend of heaps and smart balancing. Let's do a recap. We designed a structure with two operations, add a number and get the current median. Conceptually, it's about maintaining the middle of an ever-growing set without resorting everything each time. The trap is rebuilding or sorting on every insert. It's too slow. Instead, we split the data into two sides so we can grab the middle on demand. That gives us quick inserts and O1 median reads. Our plan uses two heaps, a max heap for the smaller half and a min heap for the larger half. Every new number goes to the appropriate side. Then we rebalance so sizes differ by at most 1. If both heaps are equal in size, the median is the average of their tops. If not, it's the top of the larger heap. We followed that blueprint precisely, routing each incoming number to the correct heap, rebalancing when needed, and reading the median from heap tops. We ran it on LeetCode without any errors. We verified the logic through multiple runs, odd and even counts, negatives, duplicates, and mixed orders. The medians matched expectations, and all test cases passed. The takeaway: separate, balance, and peak. By keeping two heaps in lockstep, you get streaming inserts with immediate, reliable medians, exactly the performance profile real-time systems demand.